In our first example of Barracuda NG Firewall SD-WAN, we'll have the following situation. Two firewalls connected with a TINA VPN tunnel using multiple ISPs at the same time. And at one location, we have the alarm clock, which is being filmed, and the video stream is sent onto the other location. Now, during the demo, this is the screen that we will watch. So we'll see the alarm clock. We have to watch out for any glitches or interruptions on the screen. This will indicate the eventual packet losses. We have the TINA VPN tunnel information with multiple ISPs being used, and finally the upstream throughput of the VPN tunnel. The dotted line indicates the upper limit of the throughput of the VPN tunnel. Blue colors indicates the no delay traffic of our video or voice. Green is all the regular traffic like web downloads, etc., and emails, and red indicates the packet losses that we encounter. Now let's see what happens. We see the seconds ticking by, so the clock is moving forward, and we will reduce our internet speed of both ISPs from 30 to 10 megabits per second. This configuration change will be sent and activated to the firewall. Now we have to pay close attention to the video if we see any frame drops or glitches at all, which we do. We see in the graph that the bandwidth drops from 30 to 10 megabits per second and that we have a high packet drop. So there is only a short period of time where shaped traffic takes all bandwidth, and our dynamic bandwidth algorithm from Barracuda detects this and reserves additional bandwidth for the no delay traffic, but it's apparently a bit too pessimistic or optimistic, depends how you see it, and we don't use the available bandwidth on its full maximum. But that's being stabilized afterwards. Now, if we reinstate the bandwidth of both of our ISPs from 10 back to 30 megabits per second and send and activate this configuration to the firewall, we of course again have to pay close attention to the video, and we do not see any real glitches. So there's only a very short amount of time, just a matter of a few milliseconds or seconds, where there is no delay traffic at all available. Thanks to the packet losses, the available bandwidth is being reduced. In our next example, we'll take a look what happens once we stop the video recording. So when we stop the video stream, the no delay traffic disappears from our graph. The blue disappears. We don't have any packet losses anymore, but the shaped traffic stays continuously at the same level. Once it goes to a pass-through mode, it tries to speed up the shaped traffic to its maximum performance. Now let's see what happens when we restart the video. We expect a very short amount of drop packets, and within seconds the dynamic bandwidth from Barracuda algorithm reduces the shaped traffic and frees up the room for the guaranteed bandwidth itself. We also see a performance optimization thanks to the pass-through mode of that algorithm. But in reality, our VPN tunnel runs on the internet. So we do share the network path with others that we can't control. That means that the dynamic bandwidth algorithm from Barracuda must handle bandwidth-induced latencies as well as burst rates and very short-term losses on the internet. So it's less simple than you think to program this algorithm. Now let's run our setup on a simulated internet. We add an additional firewall to our setup on which we simulate bandwidth-induced latency by using a specific command. And if we are looking back to our monitor, the VPN monitor, we see packet losses kicking in. Within seconds, the throughput of our shaped traffic is being reduced gradually until it reaches a stable maximum. And this means that the dynamic bandwidth algorithm from Barracuda is continuously feeding the firewall's traffic shaping, gradually reducing the outbound rate of the VPN tunnel. If we remove our bandwidth-induced latency and return to our lab environment by disabling this command, we do not experience packet losses anymore. Also, our shaped traffic remains kept for a while at the speed that was set by the dynamic bandwidth before. And once the algorithm enters its pass-through phase, it probes the maximum available bandwidth, and immediately the shaped traffic takes all the available bandwidth it has at its disposal. In our last demo, we'll give you an example on how Barracuda NG has implemented its dynamic transport selection. In our example, we have two transports in our VPN tunnel named bulk 0 and bulk 1. Connection object of the TINA tunnel's first choice is to send data onto bulk 1 using bulk 0 as fallback. None of the sessions will be balanced on the transports, so we'll keep our demo as simple as possible. Now the trick is to set the dynamic transport selection to best bandwidth in order to make the firewall's decision more intelligent. So in our demo, you may expect that the best bandwidth option will overrule the static configuration that we've made and eventually send the data onto bulk 0 instead of bulk 1. If we look into the connection settings of the TINA VPN tunnel, we'll see that bulk 1 is the first choice and bulk 0 the second choice. There's no session balancing configured, and the best bandwidth is set as dynamic transport selection. And once this configuration is sent and activated, we'll verify if traffic is actually using bulk 1 or if the best bandwidth option overrules this. In the live monitor of the firewall, we'll check the details of the connections, and we see that traffic is sent on B0 instead of the primary choice B1. When checking bulk 0 from the side-to-side VPN monitor, we see that the outbound rate is limited to 30 megabits per second. Now let's simulate an external change. We will reduce the outbound rate of the VPN transports so that we know that the best bandwidth will shift from B0 to B1. Going back to our VPN monitor, we see that the shaped traffic of bulk 0 is reduced to 5 megabits, and all of a sudden there is no more traffic on B0. Checking bulk 1 instead, we see that traffic kicks in at a higher bandwidth rate of 10 megabits per second. Going to our live traffic monitor, we see that all connections are still up and running, but are now being processed on B1. So this is an example on how Barracuda NG handles its SD-WAN traffic by probing the available bandwidth, looking for packet loss, and checking latency on each transport. We have greatly improved our connectivity. So I hope you enjoyed this video. If you have any further questions, please don't hesitate to contact us. You're more than welcome here at Kappa Data.